need to start. Saving the video. So today I would like to introduce a more practical set of methods, which is called Runge-Kutta methods. It is actually not a single method, but a family of methods. We are still working with chapter 4, ordinary differential equations, Cauchy's problem. And this is going to be paragraph 6, if I'm not mistaken. I don't remember. Do you think this is correct? Okay. What? Sorry. Okay. Which is called Runge-Kutta methods. So historically, the earlier family of methods was another procedure or set of procedures. So we discussed Euler, we discussed modifications of the Euler method, and most of those modifications obeyed the property that the solution at point Tn plus 1 was approximated on the basis of the solution only in one point, the previous point. We had yn and we wanted to know yn plus 1. The methods of this kind that use only the previous value of y are called one-step methods. And there was one procedure that I already mentioned that involved, in addition to one previous point, it also involved another previous point, Tn minus 1. And this procedure, we derived it from the original equation by doing the following. So we have an original equation, and we replace this derivative. With the finite difference of this kind. And at the right-hand side, we take the right-hand side function at point n, which means that we, well, I need to write y here because it's already an approximate solution. So y0 is ua, and we can express yn plus 1 through the previous values. And one specific property about this procedure is that it is not a one-step procedure any longer. It is a two-step procedure because it uses values at two previous points. The methods of this type were derived earlier than the Runge-Kutta methods by a British astronomer, Adams. I don't remember his first name. And the methods of this kind, multiple step methods, one of the subfamilies of these methods is called Adams-Bashforth family, the Adams-Bashforth methods. When people say Adams-Bashforth, they mean that the methods are explicit. So we can directly express the new value of the unknown function through some number of previous values that we already know. up to this point. And there is another family which is called Adams-Moulton methods. Those are also multi-step, but they are in addition they are in addition implicit. So on the right hand side, the very value that we want to find will be involved as well. Okay, so these sets of methods, they were derived earlier, somewhere in the middle of 19th century. And they were heavily used to predict the trajectories of the planets. But when the computers were invented, those methods were found to be somewhat inconvenient, because the computers of that time had very little memory. And in order to apply these methods, you need to remember previous solutions. If you are solving not a single equation or not a scalar equation, but a system of ordinary differential equations of high order, which is the case, for example, in chemistry, usually, because there are many components that interact with each other, and we want to predict the concentration of each of the components. Then you will have to store a lot of data. The higher the approximation order of the method, the more previous time step information you need to store. That's why people started to think how to avoid storing data. Actually, my explanation is a little bit incorrect, because Runge started to develop alternative procedures maybe not started to develop, but published the first paper in 1895. And the method that he developed used only one previous value as the simplest Euler methods, but additional calculations were involved here in this segment from Tn to Tn plus 1. So instead of storing previous solutions, he developed a method where you need to do some additional calculations in between the step you want to know and the previous step. And let's look how it works. So we will start again from the integral formulation of this problem. Let's call it problem star, initial value problem. What we mean by integral formulation? We integrate this first equation at the segment from Tn to Tn plus 1. And another thing, we assume that yn is exactly equal to the exact solution at this point. This is just an assumption that we need to make to derive the formulas of the method. So let's integrate. What do we get after integration? Integral of the derivative is just the value of the function at the two sides of the interval of integration, plus the integral from Tn to Tn plus 1 of f of theta, u of theta, d theta. And we, similarly to the derivation of the trapezoidal rule, we will work with this integral, and we will approximate this integral using different ways. But here we generalize our procedure of integration. We say that let us introduce intermediate points, some number of intermediate points between Tn and Tn plus 1 formally. They will not be explicitly involved later, but for the derivation we need to introduce them. So let's call this guy Tn1 and
so that's like Tn and Tn plus k and this.
Yes, I will write the formula in a second. And so on, and the last point will be what? Tr. So the expression for these points will be Tn first is Tn plus alpha 1 tau. Tau, just to remind you, tau is our time step. Tn second is alpha 2 tau, and so on. So on down to Tn r, alpha r tau. And here we say that alpha 1 is equal to 0, obviously, and then every next alpha is smaller, is larger or equal to the previous one, which is equal to less or equal to 1. Actually, less or equal. It's not necessarily equal to 1. So from this assumption, we can say that the previous like this will be true. So using these additional points, we can approximate our integral. Let's name it integral I capital. We can approximate it as a sum of the function values at our new points. No, it's not the approximate, but the exact solution. Here, u of t n I multiplied by gamma for I from 0 to r. From 0, I'm saying 0, no, not 0, 1, oh, for sure. Okay, and this formula is not exactly correct. Now I need to multiply it by the text. Well, I could include this factor into every gamma, but classical formulas are usually written in this way. Okay, so we just use some quadrature rule to approximate this integral. Okay, but the problem still remains. We don't know our solution at the points Tn second, Tn third, and so on. We still don't know the exact solution, right? So we need to deal with this somehow. Well, let's do the same thing again. Let's write the same relation again, but we will write this integral not for the whole interval, but only the top limit will be Tn ith. So let's say our unknown function at point Tn I is equal to the value that we do know, that is the same thing, plus the integral from Tn to Tni of f theta u theta d theta. And we do the second iteration of approximating this integral. I will delete this drawing because I need space. Okay, so u of Tn1 is equal to what? It is known. It is our yf, right? U of Tn second is and here approximation comes into play. This relation will no longer be exact. So I will write tau. It's better to write it individually. So beta 2, 1, some coefficient multiplied by f at the point where we know the solution, Tn1. How many brackets do I need to have here? One more. Okay, so we can calculate it, right? If we define the coefficient beta to 1 somehow. So this coefficient, this set of coefficients, and this coefficient, for now they are unknown, and we will need to define them somehow later. So currently we are just writing the skeleton of the formula. How the expression for Tn for u at Tn3 will look like? What it will look like, better to say. So 3, 1, right? Multiplied by f at which point? Tn1, again, the previous point. U of Tn1, close the bracket, plus beta 3, 2, f of Tn2. 2 is the previous point for the third one, right? And one more. So this is it for the third point, and so on. We can continue writing these formulas, and the last of them will look like this. Tn rth is approximately equal to tau multiplied by the sum of beta rj for j from 1 to r minus 1, yes, to r minus 1 of f t j u of t and j. And another trick that we need to involve here is the replacement of this guy with an approximate solution. So we denote this by yn1. Okay, it's just a definition. Yn2 will be, well, I shouldn't write it from this side, it should be written from this side, because there is an approximate equivalence here. So this guy will be yn1 again, and this guy will be yn2. And here all these coefficients will beynj. Okay, so this is our general approximate expression that we derive. So let's collect everything into one set of formulas. Yes, sure.
Just we do Runge-Kutta methods, am I right?
Runge-Kutta, yeah.
Yeah. But the question is that what's the goal of this?
We would like to get a method of higher approximation order without using this solution at previous time steps, except for only one step. We want to keep the amount of memory that we need to use when we program this method the same as we would have, or approximately the same as we would need to spend with the Euler method. Only one previous solution is stored, no more than one. But we want to get a method of higher approximation order. That's the idea. So we want to develop further the idea of the Euler method, actually. And in the beginning of today's class, I mentioned that there was an alternative approach to this problem. People used an approach where they stored many previous values of yn minus 1, yn minus 2, and so on, down to yn minus k-step method. But programming this kind of method will require that you store all this data. And if you are solving not a single equation, but a system of equations, it will be a substantial amount of memory. Okay, that's why Runge-Kutta methods are especially attractive in the era of computers. And in some courses, Adams methods are not taught at all these days. But they have their own niche, those methods, Adams methods, because they are very accurate. And if you need to predict your solution for a very long period of time, like a trajectory of a planet for several billions years ahead, you want to have a very, very accurate method to avoid error accumulation. Then Adams' family of methods is preferable. Okay, let's continue. So, the only thing we need to do with all this is to summarize all our derivations. I will delete this formulation of the original problem. So let's say, no, it's not gonna write. let's denote by ki the value of our right hand side at point tni, y and I for all I from 1 to r. Just a definition again. Then, using these new coefficients k that we just introduced, we can rewrite all previous formulas like this. N1 is equal to yn, N2 is equal to yn plus tau beta k1, and so on. Explicitly to avoid misunderstanding. So tau beta r1 k1 plus and so on plus beta r minus 1. Am I correct? Yes, I am. K r minus 1. This is the last term. Okay, and so we can say that. Let me check that. Just a second. So this can be. Yes. So if we put these guys here in these expressions, we have to delete this. So we get a set of equalities for the coefficients k. Let's write them explicitly. F, T, N, Y, N. This doesn't change. But the second guy is like this. I'm substituting the formula for Tn plus for Tn first through the T. I'm substituting the formula for Tn's through the previous T's and formulas for these guys. Okay, Yn plus beta 2 1 tau k. Okay. And the last formula reads Tn plus alpha r tau Yn plus tau sum j from 1 to r minus 1 beta rj kj. And the last summarizing expression should be written like this. Yn plus 1 is equal to Yn plus this guy. And here I put instead of f, I will put k I coefficients. Yes, that's it. So here is how we obtain the general form of the Runge-Kutta method. So So what we know here and what we don't know here. We know we need to define these alpha coefficients. We need to define these beta coefficients. And we need to define these gamma coefficients. These are things that are usually tabulated for every different Runge-Kutta method. Every method of this family. So how these coefficients are obtained?
So the idea of the k-step methods is to define the previous k steps, so we should know the first k values of our function.
I'm not sure why you are saying k.
No, it's not about Runge-Kutta method, it's about old methods that
Adam's
use
methods.
memory.
Could you say it again, please, what you just said?
We need to define first, for example, k values of our function.
Yes, definitely, exactly. To start, if we currently we are not talking about Runge-Kutta, we are talking about the different family of methods, which is called k-step methods, like the Adams family. So, if you want to use the k-step method, you need to define first k solution somehow. And this is one of the most criticized properties of this family of methods. Because you don't know k values of y in the beginning for k moments of time. You need to use some other procedure to start. For example, as a simplest approach, you can use explicit Euler method. But this is very inaccurate.
Yeah, that's why, but if we just put the explicit Euler method to like another formula, it means that we just store only one value anyway.
I'm not sure I understand what you're saying. So, Adam's methods.
I mean, if we have formulas just for k previous k steps, it just and anyway we should evaluate it from other values. It means that we just know only one value.
Just a second. So, what should I write here? N plus 1 minus k, if I'm not mistaken. To start with k-step Adams method, you need, and if you want to calculate value at this point, you need to know values at these points. And how can you get them? You can use like Euler method to define all these values from the previous value that you knew before.
Yeah, so we just store one.
Yes, while you are doing this, you are storing only one set of solution, one solution.
Yeah, but anyway, if we need to, we just anyway we would store all these values because we just need them to plot, for example.
No, you can plot incrementally.
Uh,
Plotting is a it's a luxury thing. You can plot it incrementally. As you get one value, you put 1 point on the plot. It's not a problem. You don't need to spend memory
okay, I see
just
that,
for plotting.
for these key values, we use another methods from.
Yes.
After these key values, we use another.
Yes, sure. If you decided to deal with Adam's family of methods, you need to decide how to get the first k values. And this is not an easy decision usually. Because Euler method is very poor solution. Euler method is very inaccurate. So if in the beginning you have spoiled your solution generating the first k values using very inaccurate method, then independently of the accuracy of your final method, you will have this problem for the rest of your life. So for the whole for the whole tail. Okay, that's why it's very important to use very highly accurate method at this step when generating the initial values. And usually people use Runge-Kutta of high order. At least the same order with the order of the method, of the multi-step method that you're going to use. So it was just a side discussion to our current discussion. Okay, so I wanted to delete all this and try to explain how to get these coefficients. For sure, these coefficients are already tabulated for many kinds of Runge-Kutta methods, for many different orders of Runge-Kutta methods, and this R here, by the way, R is called stage. The stage, or the number of stages, better say, to differentiate it from the number of steps. So, by the word step, we denote the situation when we need to store data at previous time moments, and the number of formulas that you need to calculate before you will be able to calculate your actual solution that you want to know is called the number of stages. So Runge-Kutta may be an R stage type of Runge-Kutta methods. So how to get the coefficients? Let's define a quantity that's called a local error. Local error on step n+1. So if at this point the solution was exact, what's gonna be the error at this point? U at tau n+1, at t n+1, sorry, minus y n+1. This is, by definition, this is the local error if the solution at the previous point was exact. If it was not exact, this expression will not define the whole error that you have, right? So earlier we said that we can expand our solution at the new point into series around the previous point. I will need at least up to the third derivative. I will need this formula, and maybe even more, but we'll write it later if we need it. Okay. So what I want to do is I want to expand this error actually into series, and make sure that the number of that some certain number of components in this sum will vanish. So what I do is I say epsilon of t is equal to y. Well, the same thing I've already written. I just continue here. Minus. And here I have this expression for n+1. Okay, so I just substitute this expression for n plus 1 here. And here I substitute this expansion. Okay. So what I'm doing is I'm expanding the error. This index will denote the derivative, the order of the derivative. At point 0, because point 0 in terms of epsilon, function epsilon, will correspond to this point. Got it?
Yeah.
I factorial by tau to the power of I plus epsilon p plus 1 derivative at some point theta tau divided by p plus 1 factorial tau p plus 1. This is the remainder, remaining term in the Taylor expansion formula, where theta is somewhere from 0 to 1. And I want all these guys to vanish.
Why?
I want to adjust these coefficients in such a way.
No, why when we
Well, it is just an expansion, a Taylor expansion of some function. Epsilon is some
I
function.
think it's equal to U tau n plus 1 minus this. No?
I'm not sure I understand what you mean.
Ну вот вначале мы написали, что мы вычитаем, и я думала, что это вот это мы будем.
Yes, but I don't want to, so the board is small, so if I start to write long formulas here, I will get out of space very quickly. So I'm writing an idea of what we are doing. We are expanding this error around 0. Okay? And you will be able to put the actual formula for the ith derivative of epsilon easily yourself, because here is ith derivatives, for example, first derivative or zeroth derivative is just value of function u at tn minus this guy. Okay? The second derivative, the first derivative will be this term minus what? Minus, and here, this guy, because this is the derivative of y. According to the original equation, this is the right hand side, and the left hand side will have a first derivative. You follow?
Yes.
Is this idea, is the idea clear?
No.
Okay. Okay, so I will write it by words. We adjust the coefficients alpha j, beta I j, and gamma I in such a way to make p terms Did we have a formula star in this paragraph? No? Then I can use star. In such a way to make p terms in formula star to be 0, to become 0. Is this idea clear for everyone? We will adjust these coefficients here to make these terms 0, so that only the remainder is still non-zero in our formula for the error. This is how we make, or this is how we develop a new method with the approximation order p, with the error order of order p plus 1. Okay, maybe one example, one particular example. What can I delete here? I can delete these formulas. Example. Let's take a very simple example. Let's take p equal to 1. So we want to get a method of which order? So that the local error of this method will be of the order 2. But it's the local error. It's important, not the global error. And how many steps do I want to use? How many stages, I'm sorry, how many stages do I want to use? No, let's try one. The smaller the better, right? Let's try to develop a method that has the same number of stages as the required order of the local error minus 1. Okay? Epsilon of tau will look like what in this case? Can anyone tell me what this formula will look like when p is equal to 1?
From 0 to 1,
Epsilon 0 is what? It is u at Tn.
But we...
Что?
Как будет звучать?
Subtract.
Yeah, but we subtracted UTN, no?
We subtract,
Because
to
it's
calculate epsilon 0 of tau, we subtract from u at point Tn, we subtract
EN because, but we suppose that UTN equals to UN, YN.
exactly. That's right. Which means that it is always equal to 0.
Yes.
And we can get nothing from this. It is, no,
Why
we
not?
don't need to adjust anything.
Yeah, but we have for epsilon tau, we have other terms.
Yes, right. Exactly, and we'll continue for sure. This is 0.
0, it means just the...
0 is derivative, so the function itself.
So it's not a derivative from epsilon, it just what power of derivative in...
Yes, but yes, you can think of this this way. Out of this way. Okay, and for the epsilon 1, what do we get? We get the first derivative. To say that, yeah, we can write it this way: Tn plus tau with respect to tau minus. This guy is already used here, this term. So if r is equal to 1, from this formula we only have tau gamma 1 k1, right? Minus tau gamma 1 k1. And who is k1? Yes. So here we have f. Here we have f of t n plus tau u u of t n plus tau. Do you agree? From the original ordinary differential equation. In the original equation, we have first derivative is equal to the right hand side. Okay, I've just used this original equation here. Minus tau gamma 1 f, and we recall what k1 means. Tn yn. I should have written this thing here. So I want this at tau that's equal to 0. So if I take it at tau equal to 0, at tau equal to 0, at tau equal to 0, then I get what? F of t n y n, because they are equal, minus tau gamma 1 f of t n y n. And I want this to be 0. This I want. Okay?
But tau is 0.
If we
Just a second.
choose.
Just a second.
You should just
No. I've made an error. Yes, I should have differentiated here by tau. Sorry. Misleading. I'm misleading you. I should have taken the derivative, and tau disappears. First derivative with respect to tau. Tau should be
so
should go out.
the first derivative of epsilon is kind of is it derivative or just
First derivative of epsilon with respect to tau.
and we just exclude higher orders of derivative of the t n plus 1 approximation from the epsilon,
What do you mean by higher order?
like second, third derivative.
We don't consider them because we have set p to be equal to 1 here. We have all those derivatives in this term, higher order.
Okay.
We just say that we are using the formula of the accuracy p that's equal to 1.
No, в общем, производная первой степени
Так.
по эпсилону. У нас же вот это, значит, до этого мы определили эпсилон как разницу между вот аппроксимацией функции utn плюс 1 минус вот наш метод. И там, если мы вычитаем, то у нас уходит только нулевая производная и остаются все остальные производные. То есть мы берем везде производные.
Not sure I maybe I'm not explaining clearly. I'm sorry. So if you take zeroth derivative, it means that you are writing the function itself, which is the difference between this formula and this formula. Okay? Just difference. This minus this.
Okay, I got it.
And then you take tau equal to 1, to 0.
We take a derivative
all those derivatives go out
Okay.
in this expression. I'm sorry, I misled you. It was my explanation that was not clear.
Why this part is azimuth tan equal to 0? Tan is always equal to 0. Yes.
No.
No? but why is equal to 0? I don't understand.
This is the expansion of this function, epsilon, that depends on tau, on the time step.
Yeah.
This is the Taylor expansion of this function.
Yeah.
So an infinite series, right?
Mm-hmm.
But we can make this a finite series if we use the remaining term in some form. I don't remember what the name for this form. It's probably form of piano or for Cauchy. I don't remember. But if we take this form of the Taylor expansion, I can try to adjust this free coefficients in such a way to make all previous terms 0. Okay. This is a function. This remains to be a function even if it is expanded into series. It's not a single value. It depends on tau.
Mm-hmm.
But when I adjust the coefficients,
Mm-hmm.
what I do is I'm using these terms.
Oh, okay.
These terms are calculated at tau equal to 0. Tau equals 0. Okay?
Yeah, okay. Oh, we just use this and.
And we are just writing these terms separately, one by one.
Okay.
Epsilon 0th, epsilon first, and so on.
Okay.
And but if we take p equal to 1 and r equal to 1, we only have two of them. Only have epsilon 0th and only have epsilon 1 first.
Mm-hmm.
Then let's look at epsilon 0th. This is just the difference between this guy and this guy.
Yeah.
Okay?
Yes.
Taken at tau, that's equal to 0. This difference is taken at point tau, that's equal to 0.
Okay.
Because there are multipliers involving tau in all terms here and in all terms here, except for the zeros term.
Okay.
All those terms with tau in them go out, and we only have two values: u at point tau, at point tn, and yn.
Mm.
And we assumed in the very beginning that these guys are equal.
Yeah.
So we don't need to adjust any coefficients to make them equal.
Okay.
This is just true.
Okay.
Okay? And we have only one remaining coefficient, gamma 1.
Okay.
This is how we will find gamma 1. Gamma 1 is equal to what? To what?
Oh yes, we want it to 0. So.
We wanted this guy to be 0 at point tau equal to 0, and this leads us to the solution. Gamma 1 is equal to 1. Okay?
Okay.
So what kind of formula did we get? Let's write it down. The formula yn plus 1 is equal to yn plus tau, r is equal to 1, multiplied by 1 by k1. And k1 is f of tn yn. Do you recognize this guy? Who is this? Euler, explicit Euler's method. We've just derived the explicit Euler's method if we take p equal to 1 and r equal to 1. We are running out of time. So you can do the same exercise taking p equal to 2 and r equal to 2. The result will be much more interesting. if you continue this procedure with these values, you will get not a single method, but a whole infinite family of methods, because there will be one parameter that will remain free. You will be able to choose it as you like. So the system of equations defining alpha, beta, and gamma will not be closed. There will remain one parameter that you will be able to choose as you like. That's why this decision will generate an infinite number of Runge-Kutta methods. And several of them you already know from the previous lectures. They are trapezoidal rule, they are modified Euler method, and many others you can generate yourself. This same procedure was used to generate the most known and appreciated method or family of methods with p equal to 4 and r equal to 4. They are usually called RK4, Runge-Kutta 4 methods. It's not a single method again. There will remain several parameters that can be chosen as you like. But people usually choose them to get some extra properties from the method, like some extra accuracy for some specific problems or things like that. So one last thing that I need to mention today regarding the Runge-Kutta methods is how the coefficients are tabulated in the books. So there will be many coefficients, as you see, and we need to use some common practice to tabulate those coefficients. So general approach was developed by Butcher somewhere in 1950s. So he proposed to use a table like this, where here we have alpha coefficients, alpha 1, which is 0, alpha 2, which will be defined by the method, alpha 3, and so on, alpha r, right? That's correct. Alpha r. Then here we'll have gamma coefficients, gamma 1, gamma 2, and so on, gamma r. Okay. And here we'll have beta coefficients, beta 2, 1, beta 3, 1, beta 3, 2, and so on, beta r1, beta r2, and so on, beta r minus 1. This is how the coefficients of Runge-Kutta methods are tabulated usually, and the method that you will I should have added letter E here. Explicit Runge-Kutta method. ERK4. This is the method that you will meet most oftenly. Its coefficients are tabulated like this. 0, 1, 0, 0. There are many zeros here, and it's a good property that because it means that you will spend less computational work. The more zero coefficients are in the method, the better. If we preserve the high approximation property and stability properties as well. And I need to define gammas. 2, 6, 2, 6, 1, 6 in the end, 1, 6, and here I need 1. That's it. So this is the method. If people don't specify which fourth order method they use, they usually mean this guy. And the table like this is called the Butcher table. Butcher tables. One note that need to be done regarding the correspondence between the number of stages of the method and the order P of the method. How they are connected. The number of stages and the order P. It would be very nice if it was like that. But unfortunately, well, once I attended a conference, internal conference in my previous company, and one guy, after some other guy made a report of his work, another guy said aloud, like, nature is cruel. If nature is cruel, that's why this idyllical picture does not continue forever. These double lines define Butcher barriers, so-called Butcher or Butcher's barriers. He proved that there is no method with five stages of order 5. It's impossible to adjust the coefficients in a way to make the order of approximation 5. And the story repeats on and on. For example, if you take 7 stages, you can only have fifth order of approximation. 7, 8, 6, if I'm not mistaken, and then will the third barrier come in, and so on. The story continues on and on with some period. Currently, the highest practically used highest order practically used method is approximately 10, order of 10. But it's for very special type of problems. For typical study problems, fourth order method is sufficient. If you need to know your solution of the Cauchy's problem for a long period of time, you may consider 6-step method or 8-step method, depending on the task. So that's it for